Okay, now that we've talked about molecular polarity, let's talk about intermolecular forces. So here's what we already know. Atoms are held together by chemical bonds to form molecules. And in terms of covalent molecules, this is done by the sharing of electrons. So in this particular example, each hydrogen is sharing electrons with the oxygen, and that's what's holding the molecule together. That's what is called intramolecular bonds, and they are very strong molecular bonds. Intermolecular forces, not intramolecular, but intermolecular forces, are the forces between molecules that are holding molecules together with each other. Right? So you have to think about the bonds that are holding you together as a human versus the bonds that are holding you together with your other classmates, for instance. These bonds are much weaker, but they still exist and they still play a huge role in chemical interactions. Okay, they're often referred to as IMFs, so you may see me reference that particular acronym there. So, chemical bonds or intramolecular bonds versus intermolecular bonds. My chemical bonds are holding molecules together within themselves. They're very, very strong. And again, within a covalent molecule, they are caused by the sharing of electrons. So intermolecular forces, again, holding groups of atoms together, specifically in the solid and liquid phases, although there are some IMF interactions in gases. They're very weak, but they're caused by what is our permanent or our temporary dipole or polarity of molecules. So this is where that polarity from earlier comes back into play. So there are three types of intermolecular forces. The weakest of which is called the London dispersion force. The second weakest is a dipole-dipole bonding, which is a bonding between polar molecules. And then the third and the strongest, although still very weak, is hydrogen bonding, and that's a very special instance of dipole-dipole bonding. So London dispersion forces, so they arise from this, what's called a temporary dipole in our atom or molecules. LDF, or London dispersion forces, are present in all molecules, polar or nonpolar. So let's look at this example here. So this actually has to do really with what I like to call the sloshiness of molecules. We have these electron clouds here, and these electron clouds can sort of be jostled from one side to another. So what happens is that in this particular instance here, atom A, for some reason, and we don't really know why, sort of moves all of the electrons to one side. You can sort of think about it if you put towels in a washer. Every once in a while, all the towels will sort of shift to one side, and you start to hear your washing machine get off balance. So in this particular case, atom A, for whatever reason, has its electron cloud sort of become out of balance. The reaction to that is to get this positive or this slight positive there. So atom B is going to shift its electrons to be closer to this positive, right? Because we know opposites attract. So if I create a positive, what's called a dipole moment or an induced dipole, on one side of atom A, atom B is going to respond accordingly. Right, and so we sort of see this slight shift. Again, you can sort of think about the sloshiness of molecules. Every single molecule does this. Now, the extent to which they do this has to do with how big they are. The bigger you are as a molecule, the sloshier you are. So you have a greater ability for London dispersion forces. Okay? And here's an excellent example of this. Although they are the weakest, They do vary among molecules. The larger you are, again, the sloshier you are. And so this is reflected in melting point. CH4 is a really small molecule and of course not very sloshy. It doesn't have a huge electron cloud. And so its melting point is very, 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 very low. But as I move down, and I get these bigger atoms on the outside of my carbon, my molecule becomes bigger, which means my electrons can slosh more, and that means that I can create a bigger London dispersion force between individual molecules. So you notice that my melting point goes up in response to an increase in London dispersion forces. Okay, so my dipole-dipole interactions look like this. Let's first remind ourselves of what a dipole is. So a dipole is just a polar molecule, right? So I see a positive end and a negative end. Again, here, remember, I have my electron cloud. Okay, so it's an imbalance of my electrons, right? My electron distribution is a little bit higher here where my electron clouds are, as opposed to the hydrogen side of my molecule. Okay, a dipole-dipole attraction works very much like magnets do. Instead of being a temporary shift in electron clouds, there is a permanent imbalance within my electron cloud. So my polar molecules sort of line up in this way where my negatives, the negative end of my molecule is going to be interacting with the positive end of two other molecules or three other molecules, sort of depending on where it's positioned, right? It's that idea of opposites attract. If I've got one negative sign, it wants to line up with a positive side. So if I see, for instance, HF, right, as a molecule, I know that this side is slightly positive, this side is slightly negative. So if it lines up with another HF, it's going to line up in this way, where that slightly positive hydrogen is going to try and be close to a slightly negative fluorine, right, so that I can have that electrostatic attraction. It's all this. It's all opposites attract. That's all dipole interactions are. If I have a polar molecule, then I'm going to experience this dipole attraction, as well as the London dispersion, right? Because every molecule experiences London dispersion forces. So again, here's an excellent example. I can see my positive end here is being attracted. Let's use this positive end. This positive end is being attracted here to this negative end, right? But it's being repulsed by this other positive end there. So hydrogen bonding, or our last type of intermolecular force, is a very special type of dipole-dipole attraction that only occurs when a hydrogen is directly bonded to a fluorine or oxygen or nitrogen. I like to say this is a way to remember it. Hydrogen bonding is fun, right? So I have to have that HF, that HO, or that H end. And that creates a very, 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 very special bond here. So special, in fact, that it's actually the bond that holds our DNA together. So it's a pretty big deal. Here are several examples down here at the bottom. It's not a chemical bond, so the fact that it is called hydrogen bonding, I don't want you to assume that it's a chemical bond. It is still an intermolecular force. But it is coming from these extreme electronegativity differences. So I have to have that HN bond and that HO bond, right? Or my HF bond and my HN bond, right? Or some other combination. So I have to have HF, HO, HN. generally when we're talking about hydrogen bonding, we'll be talking about whether or not a hydrogen bonds to molecules of itself, right? So again, I'm looking for an HF bond, an HO bond, or an HN bond. There you go. So strongest to weakest, my covalent bonds, and this is just in terms of what does it look like in terms of energy per mole. So a covalent bond takes about 400 kilocalories per mole to break, whereas hydrogen bonding, right, the strongest of my IMFs, takes about 12 to 16 kcals per mole. Dipole is 2 to half. And then London dispersion forces are less than 1 kcal per mole. So again, these are our IMFs down here. Just as a comparison for how much energy it takes. So, determining the types of intermolecular forces. This step number 1 is the most important. And it's the way that we've been sort of leading up this entire unit. You do your electron count first, you draw your Lewis structure, you draw your VSEPR model, you check to see if there's molecular polarity. Then you start to look at, okay, based off of whether or not this molecule is polar, what are the intermolecular forces that it experiences? So if it is nonpolar, it only experiences London dispersion forces. If it's polar, it experiences dipole and London dispersions. If you have a hydrogen directly bonded to a fluorine, oxygen, or nitrogen, then it experiences all 3 of our intermolecular forces. So here is a practice. Take a second and write it out, and then we will look at it. Okay, so we've gone ahead and we've done our electron count. I've drawn my Lewis structure and I've drawn my VSEPR structure. They are the same because it is linear. I do have molecular polarity, right? So because it is a molecule, I know that it is going to experience dispersion forces, but because it is polar, it's also going to experience dipole-dipole forces. However, it will not experience hydrogen bonding because I'm not bonded to a fluorine, oxygen, or nitrogen. So I experience dipole and dispersion. Try this one. Okay, we've drawn the structures out here. Notice that when I get my VSEPR structure out here, I only experience dispersion forces here because this is non-polar. So again, because it is a molecule, I am going to experience dispersion forces, but because it's nonpolar, I'm not going to experience any other forces. Okay, let's try this one, and I think this is the last example that we have time for. Okay, here's an example of why it's super important that you draw your Lewis structure out first and your VSEPR structures. Notice here I have my Lewis structure, and then that leads me to my VSEPR structure here. I drew it a little hastily, but it does show me that this is a polar molecule. And because it's a polar molecule, it is going to experience those dipole interactions. Let's do this last one very, very quickly. So my NH3, I'm just going to skip straight to the Lewis structure here. My NH3 looks like this. I've got that lone pair up top. And so when I draw it out, not only do I notice that it is polar, so I am going to experience the dipole-dipole. Notice here that I also have that hydrogen-nitrogen bond, so I'm actually going to experience all 3 types of intermolecular forces. Let me know if you have any questions about this. Feel free to contact me, and we can go over this a little bit further.